Don't take this the wrong way, but I too wish you were still on break. Yeah, mine could have been better. You know, the best laid plans, that saying goes, it doesn't always happen. I had wonderful intentions of getting ahead. At least I was caught up. I wanted to get ahead on this and this and this and this. And then let's just say there was a death in the family, and lots of family came in town, and you know, sister and her family, brother and his family, mother-in-law, blah, blah. You don't get anything done. So it was good and bad, but nothing that I planned. So how many of you did physics? Hey, a few of you, all right. Did anybody notice or observe anything? I know somebody did, something with a Yoplait container. We got to figure this out. Did anybody notice anything out in the world, and you thought you had enough knowledge behind to figure it out, or at least, hey, you go first.
Some flower pots were stuck together, these plastic ones, because they were freezing.
You had plastic flower pots like they were nested, or? Oh, and they stuck together? So that was probably the water froze and bound them together, and you melted it. Phase change, good.
I was cleaning out the dish that I left in my room that had, some sauce on it. It was kind of stuck.
How many days had it been?
Probably a week.
Dirty dish for a week, all right.
Found it underneath my bed. Didn't know it was
Found it under your bed.
So I have a faucet in my kitchen you can take off those ones, and I was getting real close and it wasn't doing anything. I thought, well, if I can, the higher I get, the more potential energy it gets, and so the greater amount of force or pressure I put on that. So I
Clever.
lifted it above, and sure enough, I got it off all fast.
I do that when washing. I have to admit, I did it before I started thinking, oh, this is physics, this works. I observed it, now I understand it. But yeah, if some hard crusted on stuff isn't coming off my dirty dish, yeah, I'll go down further because my faucet isn't movable. And so it picks up more kinetic energy by the time it's fallen farther. And so it has a collision with the dirty dish with greater impact. There's more transfer of momentum, and it's more likely to break it off. Good job. Fire hose.
I enjoy learning to understand the difference between clean energy and dirty energy, and how the efficiency of energy. Just help me understand that whole issue, which is huge.
So you had a little epiphany on the difference between clean energy and dirty energy. Yeah. I was thinking this week one again with fluorescent light bulbs, because they're changing out all of them in this building from T12s, the fatter ones, to the T8s. They're smaller. They require less wattage, which is our next unit, but you know about wattage. More wattage is going to cost more. And they burn brighter. These fluorescents they change those out. But my area, I got like 100 back here. And where was I going with this? Oh yeah, the guy was wondering about the mercury in them. There's a little bit of mercury gas in these, some of you might have heard. And it's dangerous. You should not just throw your fluorescent bulbs in the trash, because then they go to the landfill and that mercury can get concentrated. You should dispose of them properly. Have they given us a good venue to do so? No. But we shouldn't just throw them away. Point is, they have mercury in them, yes. More than an incandescent bulb. Remember the kind that just you send electricity through it, it heats up, and because it's now hotter, it burns brighter. It emits more radiation. The hotter something is, it's proportional to temperature, that peak frequency. Well, to make that from a coal plant, the coal power plant, in processing it, puts more mercury in the atmosphere than is in one of these bulbs. To make one bulb here versus one bulb here, there's more mercury outputted than in a light bulb. Now there's different problems with each. So sometimes I wonder when they say, go green, they do require less. I'm all for compact fluorescents. They do require less energy. There is less mercury in them than over here. But that does usually end up in the landfills concentrated where this didn't. So there's always trade-offs. And the point is, it's conservation of energy and efficiency. you have to rule the advantages and the disadvantages. And a lot of people, when they're selling you something, I hope by the end of this class will be more like a scientific thinking minded person. So you won't just accept anything willy-nilly in the media when they say something. They skew results. So do some scientists. They're not supposed to. Good scientists, remember way back, first chapter? Something, it's not science unless you can test it. And even further, it has to be able to be proven wrong. A lot of things you can't prove wrong, so don't call it science. So yeah, they tell you what they want you to know, not the other side. And usually, you know, from what you've learned in this class, you ought to be able to put enough together and start rationalizing these things out for yourself. And I can tell you guys are doing that. You're being observant and seeing things. Kudos to you. So, quick review, because it's been a week. What's temperature? Average translational kinetic energy of your group of molecules. Good, good. So, you know, summing it up, the hotter something is, the faster the molecules are moving, on average. There's some slow and there's some big, and they're having collisions. Billiard ball physics. Good. How is that different than heat? Very important. Heat's the transfer of energy. Isn't temperature energy? Trick question. It's a measure of energy. Yeah, it gives you a gauge of how much average translational kinetic energy something has. Which leads to the next one. What's internal energy? The amount of heat energy in an object? And the rotational and any potential. It's all the energy in something. You got a thing of water just sitting there. It has so much internal energy, which can include all forms of energy through the molecular bonds, for its height, atomic, nuclear, all of that is in there. Where temperature is just a measure of the average translational kinetic, their motion, but they can be doing other stuff. There can be other energy there. Temperature is just a measure of one. Internal energy is including everything. When does heat flow? Heat's the flow of this internal energy, either in or out, but it depends on something. It won't flow unless there's a difference in temperature. And which direction? Hot to cold. I have a geyser going over there. It's hot enough now. I'll explain it in a moment, but we'll watch it. Little tabletop geyser. I'm putting internal energy. Let's put it this way. The hot plate is providing heat. This is hotter than the water and beaker, and so heat is flowing into our system, and it's raising its temperature. It's also going into not just raising its temperature, but what's happening to the water. You can hear it. It's boiling. The temperature does not increase during boiling. It's a phase change. That's where we're at today, once I get done reviewing. But yeah, some of the energy goes into changing it molecularly, and it goes from a liquid to a gas. That's boiling, evaporation underneath the surface. Alrighty. Then we had specific heat capacity. How do you guys like to remember this? Thermal inertia. I think that's great. Say again? Yes. Yeah, this is, technically what it's called. This helps me remember what it means. Because you guys we've had inertia all semester. Specific heat capacity. This is, it's specific to what material you have and how much of it you have. It says heat capacity, this capacity of something to allow heat to flow in or out. Again, don't think of no object contains heat. This is kind of a misnomer. It's not like, oh, this has so much capacity for heat. Because that gets you thinking conceptually incorrectly. Me too, I fall into that trap. But it does mean that it has inertia, a resistance to change. Before, in Newton's first law, resistance to change of motion. If it's at rest, it wants to stay at rest. If it's moving, it wants to stay moving. If something's at a certain temperature and has a certain amount of internal energy, it wants to stay that way. And so if you apply heat to try to raise its temperature, or vice versa, it wants to resist that thermal inertia. So something with a high specific heat capacity, high thermal inertia, like water, it wants to resist changing its temperature for a given amount of heat. You apply heat to water, sure, energy's going in, it's raising its temperature, but its temperature will not increase as quickly as if you put the same amount of heat into metal. Metal has a low thermal inertia. Its temperature will rise more quickly. This equation was a good guide to thinking. We just covered it all now. Heat, in or out, depends on how much of something you have. Remember, if you had a liter of water and 2 liters of water, who has more at the same temperature, room temperature, sitting here? 1 liter, 2 liters. Who has more internal energy? 2 liter, because there's more of it. Who has a higher temperature? They're the same. I just told you it was the same. Trick question. They're sitting in the room temperature. So they have the same temperature. That means on average the molecules are moving around at the same speed on average. But there's more in 2 liters. There's twice as many of those molecules. So you have twice as much energy total. That make sense? Don't fall into that trap. And water, what I just said, as opposed to if it was 2 liters of metal. And the temperature change is what gets heat to flow. If this is 0, no heat flows. So this kind of sums it up. What do we do next? Thermal expansion. Most of you are already familiar that when things heat up, they expand, and we did some demos, and vice versa. When they get smaller, they contract. And what's one common exception? Water when it freezes to ice. Yeah. Instead of contracting as it gets colder, it expands. Do you remember that temperature range? Volume, temperature. It was say this was 0 degrees Celsius. And we heat it up. Which way should I draw my line? Yeah, down. It's going to contract. Until what temperature? 4, yeah. And then it starts expanding again. Again, it's because water, when it turns to ice, the molecules can be closer together in water, liquid form. When they form ice, they get those hexagonal 6-sided rings with more space in between. So they take up more room. They expand. And in this region, there's a competition between, as you heat it up and those rings start collapsing, they get closer together. But they're also increasing their temperature. So they're starting to move faster and try to expand. And here, the collapsing part dominates. And over here, the thermal motion is dominating. And it keeps expanding. But anyway, water's that exception there. Good. What was next? Heat transfer. What are the 3 ways you can transfer heat once you have a temperature change? Conduction, conduction, convection, radiation. Conduction's when it's in contact, yeah. When these jostle, they bump into these guys, they're neighbors, and it conducts through the material. Convection? Flow, current. Waves, think of waves more with radiation. It's the fluid. Think of a fluid being air or water. That it heats up and it moves. The motion of the substance moves and takes the heat away. Like from a radiator, whoosh, comes over here, gets in contact with it, and there's heat transfer. But it's through the motion of the fluid, like in the sun, in water, the convection currents. What happened? Radiation, go Kate. Yeah, Heat waves coming from the sun is an example of radiation. Does radiation need a medium? No, it does not. Convection does. If you have nothing in between you and me, get rid of the air, then there's nothing to convect over to you. And we're not in contact. So it can't be conduction, can't be convection. The earth gets heated up by radiation from the sun. That's an electromagnetic wave. Think of infrared. That's in the heat. And then that leads to something, all objects radiate. The hotter they are, how do the waves differ when something's hotter than when they're colder? Say again? There you go. They emit blue light. Good, you remember that. Compared to red light. What's the difference between blue and red light? Yeah. Red light has longer wavelengths, like this. Let's say. Not drawn to scale. And blue would be more like this. So the hotter something is, the shorter its wavelength, which means it's oscillating more quickly. The frequency's higher, it has more energy. Red light compared to blue light has less energy, isn't vibrating as quickly, longer waves. And you can go outside of the visible. If you go more in this direction, you get infrared and radio waves. You go this direction with more energy still, you get ultraviolet. Black lights? Microwaves, cosmic rays, X-rays. All form, yeah.
Does that have anything to do with fluorescent lights that you can get warm or cool, which is red or blue?
Yeah, they just replaced all ours with cool. It's the spectrum they emit. A cool fluorescent emits more blue side of the spectrum, where a warm emits more of the red side. And how they do, that tells you then a warm fluorescent should be cooler to the touch than a blue one. Or at least the gas inside is hotter in a blue one than in order to emit it. It's the phosphors on the inside coating of the glass, what spectrum they give off. They coat them with different phosphors, so when they get excited by electricity goes through, it ionizes the gas inside. Do you remember what ionize means? Anybody? It came up once. Say again? It has to do with the atoms. It's not necessarily they line up, but you get rid of some electrons. Because the fourth state of matter is you got solid, liquid, gas, and plasma, as this chapter talks about. I'm not emphasizing it as much, but yeah, it's above gas. It's got even more energy. And that's when the atoms start breaking down. Electrons get ejected, and it leaves the remaining atom positive. And then you got negative. So it's charged particles. It's like a gas with even more energy and energized, stripped of electrons as a plasma. That's what happens inside a compact fluorescent tube. When those electrons recombine with an atom, they give off energy in the form of electromagnetic radiation, light. Usually it's not light we can see. It's ultraviolet, a little more energy than blue. It then hits the phosphors. The phosphors on the inside absorb that ultraviolet light, transfer of energy through radiation, and then they go through a process internally that emit their own light. Blue, red, cool, warm, whatnot. It's interesting though, but it's just a transfer of energy, and it's through radiation. So something, which is a better radiator, black or white? Well, we're going back and forth. Which is a better emitter? Oh, you all got that one. Would you rather wear a black t-shirt or a white t-shirt out in the desert? White, because it reflects heat. So is it absorbing radiation as well? No, so white is a poor absorber. But it's also a poor radiator and emitter. Black is a good absorber, because you heat up faster. But it's also a good emitter, radiator. White reflects it, so it doesn't absorb. Black does absorb. Poor reflector, if you will. Does that make sense? So things that are good radiators are also good absorbers. And his black jacket right here, is that brown?
Yeah,
It's dark. It's at room temperature right now, close enough. So is it absorbing or emitting? Thank you. Both. And at what rate? Who's winning? It's a balance again, yeah. If something absorbs more than it radiates, yeah, it's a better absorber. It's getting more heat. Its temperature is going to go up, and vice versa. So that water is absorbing more heat than it's radiating, but it's doing both at the same time. When the temperature is not changing, then yeah, they're in balance. And it doesn't matter what color it is. His white t-shirts, you know, aside from body temperature trying to, but it's in thermal equilibrium with the room. So its temperature is not changing. There's no heat flowing in or out. No net heat. Because it's constantly giving off radiation because it has a temperature. It's giving it up, so it must also be absorbing at the same rate. Environmentally, if it was a net absorber, it would get hotter and hotter and hotter and hotter. What did that lead us to? Phase changes. Made it to this chapter. Solid, liquid, gas, plasma, electrified gas, more energy. We started with liquid to gas. What's it called when you go from liquid to gas? Evaporation. And we started where that's the molecules bouncing around, and if they're at the surface, some of them, if they have enough energy, on average they have a certain temperature, but those faster moving ones can escape. And if the faster moving ones leave, they leave behind the slower moving ones with less energy. So that can cool with the liquids on. You know, if you got, that's how I remember it, sweat on your skin, as it evaporates, it's a cooling effect for you. You feel cooler because it's evaporating. It takes energy to do that. It takes energy. One molecule of water needs to absorb energy to become gas. Or think of those particles. The faster ones leave. Energy left. What, the other way? I think I heard somebody mumble it. Condensation. And the reverse. The gas molecule has to give up energy to become water. It slows down to coalesce. What's happening over there is boiling. That's essentially evaporation, but underneath the surface. The stuff at the bottom is getting really hot. Heat's being transferred, and it's vaporizing. And if that vapor pressure underwater in the bubble can overcome the water pressure and atmospheric pressure, then that bubble will continue to grow and come up to the surface, and you get boiling. If you can put more pressure on top, you can keep it from boiling, right? Because it's trying to vaporize. It's at 100 degrees C, let's say, and it should be boiling. But if you're like pushing on it, nope, wait, then it's got to raise its temperature even higher until it can boil because you're not pushing down enough. That's what a geyser is doing. This little tabletop geyser, it's just blue water. And so, there we go. Down here, the temperature is, let's see, about 200 and, it depends on where I'm at. There is 365 degrees Fahrenheit. Water boils at what Fahrenheit? 212 at atmospheric pressure and at sea level. Here it should boil a little less. But yeah, this is getting up to nearly 300 degrees Fahrenheit. Up here, it is 186. So this isn't hot enough to boil normally. This is hotter than it needs to be. Why is it boiling at this temperature? Because this extra weight is putting pressure down there. And if this was wider, we could get what form of heat transfer? Convection. And that would help keep the water temperature uniform. It would take the heat from the bottom and heat the top up. And in your pan, your water is usually the same temperature as it grows together. And so you see it boil when you think it should. But if it can't convect to transfer away some of that heat, it just gets hotter and hotter and hotter until it can overcome the pressure. And when it does overcome the pressure, what's it do? It just pushes the water that's in its way out, and there goes Old Faithful. So it's boiling down here. It's plenty hot. You can see some of the bubbles start to rise, and it just cycles. Yep. Here it comes. You can see it's trying to come out, but there, it made it. And as the gaps go through, the pressure can equalize because air can get in. It's back to normal, no pressure difference. But this is the part I like when it's done. Water drains back in. Pressure, it's closed off. Increase, increase, increase until it cycles again. Yeah, if this were taller, it would get even hotter and take longer per cycle. You go to a mountaintop, you decrease the pressure. It should boil easier. You go deeper into the ocean or into the earth, and it's harder. Does that make sense? So that's our little geyser. I can turn it off. It'll keep going for a while.
So as it gets longer and longer, when it does erupt, does that make it eruption bigger and bigger the longer it has to travel?
The longer it is, it's more because it'll get to a bigger pressure difference. So it's like a bigger bomb. You know, it's like pumping, pumping, pumping. If the release valve releases too soon, yeah, you get a boom. But if it takes longer till it releases, you can build up more and more pressure, and so it erupts more violently. And there's more water in the tube to blow out, so it would seem bigger too. It'll take more force to overcome that weight of fluid. So a really big geyser, you see, must have a big difference. It could be really long and skinny, or well, there's a trade-off between how wide it is and how much water you have. There's more weight that way, but you get more convection as well. So that's fun. I want my chop. There it is. Okay, you know this one, solid to liquid, melting. And the other way, freezing. These are more common, so I don't need to spend as much time on it, but the same game plays. It takes energy to go that way, and it releases energy going this way. So to take things bound in ice crystals, it takes energy to go to liquid. To freeze, it's got to give up energy to freeze. What's it called if you go directly from solid to gas? Sublimation. Sublimation. You know an example? Say again. Dry ice is frozen carbon dioxide. And yeah, it at room temperature, at room atmospheric pressure, it goes directly from solid to gas. It does not need to go through the liquid phase. It goes directly. Just think of it sitting there. It's the same thing as like evaporation. It just goes straight. They start coming right off the surface of the dry ice. It's fun. There's another thing your book talks about, regelation. Looks like regulation. Regelation. And that is putting some weights on a piece of ice and seeing if you can force it to melt at a different pressure. So I left my ice cube in the freezer so that it wouldn't be all melted before we do this. So give me 20 seconds. Hi class, I'm at the freezer now. So I froze a little chunk here. Why am I putting it on styrofoam instead of directly onto the metal platforms? That's right, it does have lower thermal inertia. I don't want the ice cube to melt by the heat from the metal coming into the ice and melting it just by resting on the platform. So I put it on styrofoam, which doesn't allow the heat to conduct through as quickly. So now I keep blabbering on while this is resting on top. So it's just a little thin wire on the top draped with a kilogram mass on each side. It's exerting pressure, weight, force, over a small area, cross-sectional area of the wire. So that's exerting a lot of pressure. Remember, force over area is pressure? That's why I always write the equation. Let's see. Force over area. There we go. So that's what's happening. So what's happening is the ice right underneath the wire is under more, significantly more pressure than just due to atmosphere. And you can get phase changes by not only moving the temperature around, but the pressure, as we were seeing with boiling points and whatnot. Interestingly enough, this actually lowers the temperature of the ice underneath the wire. It's going to melt the ice and work its way through the ice, but as it goes through, the water will move above the wire and refreeze. And so hopefully, if this works, we'll hear the weights go clunk onto the table because they made it all the way through the ice cube, but the ice cube will still be intact. So this increase of pressure has the effect of melting the ice at room temperature. But in reality, it actually lowers the temperature slightly, very slightly, but to the melting point. You remember your chemistry with ideal gas law and your PVT squares? Maybe you don't, but when you do the pressure, it actually lowers the temperature. I find that fascinating. But it lowers the temperature to the melting point at that pressure. The melting point's lower at increased pressure for ice. So I'll keep babbling while that does its thing. From the remaining ice. Yeah, so it's like the wire is pushing, it's getting pulled, so increased pressure right there. And that has the effect of melting the ice and it turns into water. Let's see. We go from solid to liquid. That takes energy. Where does that energy go? Into the internal energy of the ice to break up those bonds, crush those crystals, hexagonal rings, to melt. Then, yes, in general it's melting, but where it's under the wire, it's going to melt faster. You're right. Heat from the room is causing the ice cube to melt just right now. I'm trying to eliminate that because it's on styrofoam, so there's little conduction, and the air is a very poor conductor of heat. And so it is hotter in here than the ice, and so energy is flowing from the air to the ice, trying to melt it, and it eventually will. But it's slow. As you've seen by having an ice cube out, it can last quite a while. Yeah? Why does it take longer to do what? Why does it take longer to make water boil as opposed to? It's that anomaly for ice. Essentially this thing. And so that's between melting and freezing over here for ice and water. This doesn't work if you had a frozen piece of something else. Over here, though, That was with boiling and condensing. And so, different game. Do you understand why it raises the boiling point here by increasing the pressure? Does that make sense? They're trying to vaporize. No! Add more pressure, and so it'll take longer. This one, the pressure is going in to try to crush the ice crystals. But it's under greater pressure. That one has the effect, again, because of this, to lower the melting point, and it reaches that melting point and melts. It's a very, very, very small shift, mind you, but after that, so it melts underneath. Well, then the water can flow up around where there's no pressure anymore, less pressure. And so it goes past the melting freezing point back and grabs the heat from the remaining ice and refreezes above it. So the increased pressure melts it underneath, it flows around, no more pressure for that water, and it refreezes. It's a cool effect. Yeah? It's colder underneath. Yeah, the temperature actually drops very slightly. Because it drops to the melting point. The melting point's different. Similarly, the melting point's at a different temperature when things are at a different pressure. Likewise, for water, well, actually for anything, the melting/freezing point is at a different temperature for different pressures. In this case, when you increase the pressure on water, you can reach the melting point. Oh, gee. Finish off the chapter or a few questions? Oh, you got a preference? All right, I'll draw a graph. That's what I'm going to do. This is in your book if you don't want to have to follow me along here. Let's say this is minus 50 degrees, 0, 50, 100, whoa, that's not what it, 0, 50, 100, 150. So we got temperature in Celsius, and we're going to add heat. In calories. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's far enough. All right. We're going to start right here. What form is it in? This would be at normal pressure. Solid. Let's call it water. We'll work with H2O, so ice. There we go. We're going to add heat. Say it's on a hot plate. And it'll rise to 0 degrees. Then what happens? Does it keep rising? Depends. That's true in real life. It stays the same, but we're going to keep adding heat. So what's going to happen to this ice? Yeah, it's going to phase change. There we go. Oh, sure. As it fell, it cracked it because of torque. But anyway, it made it through. Then it torqued it and broke it, so it doesn't seem as impressive. You have to trust me, or you can try it yourself. It went, this one looked like it made it, like the last millimeter or two. And then it just kind of cracked it like you can if you just go like this, because there's lots of weight on it. But it almost made it all the way through from what we were talking about. Anyway. Regelation. All right, so yeah, that's my point. It's going to be, it's going to melt. Then, it's now water, and its temperature, as you add heat, the temperature, let's see, maybe about, trying to be somewhat to scale here. Gets up to 100 degrees Celsius, and then it starts to boil. And that gets all the way over to about here as it converts to gas, steam. Then its temperature keeps climbing again. To put some of this in, the very last thing in this chapter has to do with latent heat of fusion and latent heat of vaporization. We've been talking about it, they just give terms to it. This works when there's a temperature change. Allows heat to flow. If there's a temperature change, heat will flow. But what if you're forcing heat into something and the temperature is not changing? You're putting heat into it, but the temperature is not changing. What must be happening? It's a phase change. So there's this one more little equation to figure all that out. And it is that. It depends on how much of it you have. You know, you got more ice, it's going to take more heat to melt it all. And this L, which is called the latent heat of fusion or latent heat of vaporization. And that just depends on which phase you're going in between. If you're going over here, then it's latent heat of fusion. If you're trying to go for between solid and liquid or liquid to solid. And vaporization over here. Does that make sense? And so your book gives you some values, and I find this interesting. So in this section, Q equals MC delta T. We'll make this math easy. Let's say we have 1 gram of water, ice, 1 gram of ice. Its specific heat is, I give that to you, a half. And we're going to raise its temperature 50 degrees. Do you see that? How much heat did that take? $25 calories. So if we take 1 gram of ice and give it 25 calories, we can melt all of it. Not melt. We can get it up to its melting point. Sorry. In this section, we're going to take that 1 gram, and the latent heat of fusion for ice is, I wrote it down, 80. So it's going to take 80 calories just to melt it. Do you see that's a lot more to melt the same amount of material than it is just to raise its temperature 50 degrees. So the ice has to absorb a lot of energy. It takes energy to melt. So you got to put heat in. Then of course it starts, we're now water. We got the same 1 gram. The specific heat for water is 1. And we're going to raise it 100 degrees. So that takes 100 calories. Just a little bit more than it took to melt it, just to get it up 100 degrees. And now we're going to vaporize it. So up here, 1 gram, and the latent heat of vaporization is, for water, 540. So it takes a whole lot more heat to turn 1 gram of water into steam than it does to do anything else. And then we can go up and up and up. I'm not going to. It's similar to the ice. So that's how you would play this game with heat. We're not going to have to get that mathematical, but simplistically, I want you to realize you can do this. You just know whether it's changing phase or not, how the heat is being transferred. And it takes significantly more energy in the phase changes. This is why you can get burned so badly with steam. Realize if you have steam at 100 degrees Celsius, and water at 100 degrees Celsius, which is more dangerous? Steam. Because no, you're right. I'll come back to condensation. Let me ask you this. Who has more internal energy? Yeah. And a whole lot more. You see that? So back to yours. Yeah, you put your hand in the boiling water. Sure, that's going to hurt. Not a smart idea. But you put it right into steam. It's going to try to condense on your hand because it's cooler. You're taking heat away from it. You're slowing them down, the particles. And so energy is going to be given up from the steam into you. But before it can drop its temperature, it has to become liquid in the first place. And so just 1 gram of steam condensing on your hand is going to release 540 calories of heat energy. And that's going to go into you before it ever starts causing the water then to cool down. You follow? So yeah. So that means gas has a whole lot higher internal energy than liquid, and it more than solid, and thus plasma has the highest amount of internal energy as the fourth state of matter. It's on this side. It's going to take even more energy to get to that point. Oh, it's because I threw it over here. There we go. A few minutes left. You want to see an unrelated demo? It'll only take a minute. This is our next unit after heat. Your friendly reminder, Wednesday and Friday, we're going to cover the last chapter, chapter 18, on thermodynamics. Next Monday, we'll review. And next Wednesday, on the 28th, we'll test over all this heat and temperature stuff. Then we're going to start chapter 22. In your book, it's electricity and magnetism is where we're headed. Here's one demo. The next class was going to do this, and I thought, what the hey? What color is this LED? I hear yellow and orange. That's good. Are you sure? It's cooler with all the lights out. Close enough. These are 2 LEDs. One's red and one's green. And this is AC current, alternating current. That means it changes directions. Half the time it's going one way and increasing and coming back down to 0. And so it's flowing one way. Let's say that's the red light. But then it goes negative and flows the other direction. Increases, come back to 0. And that's the green light. Alternating current. Notice what's in between the red and the green. Black. That's what the power company's gypping you. Not really, but technically it's AC current. It's alternating, changing directions. And for a brief moment, really fast, this happens 60 times every second. That's what we do in the United States, up and down. But for a real brief moment, you're getting no power because the current is changing directions. Just like velocity, when something bounces off a wall. So that's where we'll be heading after heat. Have a great day.